Hi everybody. Welcome to the last session of ALIA. In fact, one of the last sessions of the entire conference. Thank you for being here, the last survivors of the last day. We know it's not easy. In this session, we are going to have three presenters, beginning with Mauro Castelli, presenting a hybrid genetic algorithm for a longest common subsequence problem variant.
So thank you, Sara. Good afternoon to everyone. I am Mauro Castelli from ISEGI, Universidade Nova de Lisboa. And the title of this work is a hybrid genetic algorithm for a longest common subsequence problem variant. And the other authors of this work are Stefano Beretta from University of Milano Bicocca and Leonardo Vanneschi. So here we have the outline of this presentation. I will start by presenting the repetition-free longest common subsequence problem. It is the variant of longest common subsequence that we consider in our work. Then I will speak about the computational complexity of different instances of this problem. I will briefly present existing algorithm that approximation algorithms that have been defined in order to address this problem. Then I will present our algorithm that basically makes use of genetic algorithm and estimation of distribution algorithm. And finally, I will conclude the presentation by discussing the experimental results and suggesting some possible future works. So the problem we are interested in is denoted in this presentation with RFL-CS. It's called repetition-free longest common subsequence. So the problem consists in the following. Given two sequences, X and Y, that are defined over a finite alphabet sigma, we want to find a repetition-free longest common subsequence of X and Y. That is an LCS between X and Y with no repeated symbols. This is an important and well-known problem, in particular in the field of bioinformatics, and several analyses about the computational complexity of different type of different instances of this problem have been considered. For instance, in the work proposed by Bonizzoni co-authors, several variants of the RFL-CS problem have been considered, and in particular, authors studied the case where some symbols of the alphabet sigma are required to appear in the South LCS and possibly more than once. It is possible to prove, and authors prove, that these variants of the RFL-CS problem are API-hard, and in some cases it is a NP-complete problem just to decide if an instance of this variant is feasible or not. So this complexity result makes this variant less tractable, but on the other hand, we have also there exist some polynomially solvable instances of the repetition-free longest common subsequence problem. In particular, if each symbol of the alphabet appears at most once, either in the sequence X or in the sequence Y, in this case, the problem is very simple. It's quite simple because it's enough to find a solution for an LCS problem of X and Y. In fact, in this case, any longest common subsequence has no repetition, so it is clear that it is also a solution for the RFL-CS problem between X and Y. Given that there exist polynomial algorithms that compute the LCS of two sequences in polynomial time, this case is polynomially solvable. So given the importance of the problem and the different computational complexity of different instances of this problem, several algorithms have been defined in order to address this problem. Before describing existing algorithm, I need to introduce some definition that I will use in the remaining part of the presentation. So for each symbol A of the alphabet sigma and a sequence W, we denote with n of WA the number of occurrences of the symbol A in the sequence W, while we denote with MA of XY the minimum between the number of occurrences of the symbol A in the sequence X and the number of occurrences of the symbol A in the sequence Y. The previous case, so the case in which each symbol appears at most once in X or in Y, is the case in which MA of XY is equal to 1 for all the symbol A of the alphabet. So if we consider the general case in which MA XY is greater than 1, it is possible to prove, and it has been proved in the work of Bonizzoni and co-author, that the problem RFLCS is EPIX complete even when restricted to instances of the problem in which the number of occurrences of every symbol A in X and Y is bounded by 2. So several, as I told before, several approximation algorithms have been defined in order to solve this problem. And here I will briefly describe 3 existing and widely used algorithms that in our work we use to make a comparison between the performances of our algorithm and the performances of existing ones. So the first algorithm that I denote with algorithm A1 consists of the following step. It's a very, very simple algorithm. So considering 2 input sequences X and Y, the algorithm computes an LCS of X and Y. Then it randomly removes all repeated symbols but 1 in the obtained LCS. And finally, the algorithm returns the resulting sequence. If we denote with M the maximum value of MAXY, it is clear that this algorithm is an M approximation for RFLCS of XY. The second algorithm, also in this case, is a very simple probabilistic algorithm. So given the 2 input sequences X and Y, for each symbol A of the alphabet, the algorithm, if MAXY is equal to n of XA, the algorithm picks at random one of the occurrences of the symbol A in the sequence X and delete all the other symbols from the sequence X. While in the opposite case, the algorithm makes exactly the same operation on the input sequence Y. So after this cleanup operation, if we denote with X prime and Y prime the resulting sequences, the algorithm just compute an LCS W prime of X prime and Y prime and return this LCS. Finally, the last algorithm that we consider in our work is a variant of algorithm A3, but in this case, differently from algorithm A2, in this case, instead of choosing one of the occurrences of each symbol in the sequences, the algorithm A3 picks uniformly at random only one number in the range 0, 1 and uses it to decide which occurrence of each symbol will remain. And the same number, that is the difference with the previous algorithm, is used to select each of the occurrences of all repeated symbols. So basically we have 3 simple heuristics that have been used in order to solve the RFLCS problem. So our proposed algorithm makes use, as I told before, of genetic algorithm and estimation of distribution algorithms. In particular, the GA is used to explore the source space, while the estimation of distribution algorithm is used to to guarantee the constraints of the problem. In particular, as I told before, we want a longest common subsequence between X and Y, where there are no repeated symbols. So basically the algorithm works as follows. So given an initial population P of n chromosomes, the standard GA is used to build a new population of candidate solution. In particular, an individual or candidate solution is represented as a binary string where each bit indicates whether or not the character in position I of the first input sequence, denoted with S1, must be considered in the common subsequence between S1 and S2. S2 is the second sequence in input. So it is clear that if you use the standard GA and the standard crossover and mutation operator, it's not possible to guarantee that a particular symbol will appear only once in the common subsequence. In particular, conflicts may arise. Here I reported the definition of conflict. So let's denote with S1, the first input sequence, and if we consider a candidate solution K, we say that a conflict appears in the individual K if both of these conditions hold. In particular, the first condition is that Ki should be equal to Kj should be equal to 1. That is, the character in position I and in position J of S1, okay, should appear in the common subsequence between S1 and S2. But, and this is the second condition, the two characters are the same. So we have a conflict because, I repeat, we don't want a repeated symbol in the final longest common subsequence. So, to resolve potential conflict that may appear, the idea is to estimate the distribution of promising solution using an ADA, assuming that the variables in the problem are independent. In particular, the model of the selected promising solution contains a set of frequencies of all values on all string position in the selected set. So basically we build a model that is represented with a vector of frequencies that is used to resolve conflicts that may arise in the candidate solution. In particular, if a conflict appears, it's solved in the following way. If y is greater than vj, then kj is set to 0, while in the opposite case, ki is set to 0. In order to build this model, this vector of frequencies, we use a very simple algorithm. So we start with an empty array of size L, initialized with zeros. Then we select a subset of candidate solution Q from P based on fitness, where in our application, in particular, we select half of the population. Then for I equal to 1 to L, and for each chromosome in the subset Q of P, we update the value of Y, and finally we calculate the frequencies. So basically the resulting algorithm is the following. We start with a randomly generated population of n L-bit chromosome, where the conflicts are randomly resolved, because after the initialization we don't have any kind of information in order to resolve conflicts. Then we calculate the fitness of each chromosome in the population. Then we have this evolutionary loop. In particular, we repeat this step. We select a subset of chromosome from the current population, and the probability of selection is an increasing function of the fitness. As I told before, in our application, we use half of the population in order to build the model V, the frequency vector V. Then, again, we consider the initial population P. We apply selection, crossover, and mutation in order to create a new population P prime. We update the elements in P prime, resolving the existing conflict using the information contained in the model V, in the frequency vector V. And finally, we calculate the fitness of the elements in the new population. So, as I told before, our algorithm was tested against the 3 approximation algorithms that I have just described on randomly generated instances of the RFLCS problem. In particular, in order to generate these instances of the problem, we consider 2 parameters. The first one is the length of the sequences, and the second is the alphabet size as a function of the sequence length. Each position of a randomly generated sequence is, of course, one of the symbol of the alphabet, and each position contains a symbol that has been randomly selected. So in this way, we have that in these input sequences, most of the symbols have approximately the same number of occurrences. Here I reported the experimental setup. In particular, for each combination of sequence length, value, and alphabet size, we perform 30 independent runs. We have considered 5 values of the sequence length parameters, so L equal to 32, 64 up to 512. And for each of these value, we have considered 7 different alphabet size that are function of the sequence length. All the runs that we perform use population of 100 individuals, and the evolution stopped after 1000 generation. And the candidate solution are represented as binary string of length equal to the length of the input sequences. To create new individuals, we simply applied 1-point crossover and flip mutation with probability of 0.9 and 0.05. So regarding the fitness function, so as I told before, an individual of the population is a string where each bit indicates whether or not the symbol in position I of the first input sequence must be considered in the common subsequence between S1 and S2. And in this case, we have that the bit is set equal to 1. So now, in order to calculate the fitness, we consider a subsequence S1 prime obtained from the sequence S1, considering only the character S1i that such that the chromosome has a bit equal to 1. So S1 prime contains the symbol that should appear in the common subsequence between S1 and S2. In order to calculate the fitness is defined as the length of the LCS between S1 prime and the S2 with a penalty factor that considers the number of characters of S1 prime that are not in the LCS between S1 prime and S2. So basically we have this fitness function in which we have the first factor that considers the length of the LCS between S1 prime and S2, okay, minus the penalty function that basically return 1 if a particular symbol, okay, does not appear in the common subsequence between S1 prime and S2. Here I reported the result, in particular the length of the obtained repetition-free longest common subsequence, considering different length, okay, and different alphabet size. But the most interesting results are reported here in this table, in which we have a comparison with between our algorithm and the 3 existing and widely used algorithm A1, A2, and A3. In particular, from this table, it is possible to see that our method and also algorithm A1 are the best performer, while algorithm A3 is the worst algorithm among the techniques that we have considered. In particular, if we compare our method with algorithm A1, we can see that our algorithm produces the best performance with a value of the sequence length parameter from 32 up to 128, while for increasing value of the sequence length parameter, we have that algorithm A1 is the best performer. If we consider our algorithm against A2, we have that A2 is better than our algorithm for value of the sequence length parameter greater than 256, while algorithm A3 is always the worst performer. So also in the table, I reported with the dark gray the length, the longest common subsequence, the length of the longest common subsequence. So finally, to summarize, in this work we propose a variant of the longest common subsequence problem called repetition-free longest common subsequence. This is an important combinatorial problem, in particular in the field of bioinformatics. And this problem has been proved to be NP-hard and also APX complete. We propose a hybrid genetic algorithm which combines standard GAs and ADAS to solve this problem. In particular, we test our algorithm against 3 well-known and also widely used heuristic algorithms that address this problem. And experimental results show the suitability of our algorithm in addressing this kind of problem. In particular, as we have just seen, we have that the proposed method produces the best result for small values of the sequence length parameter independently from the alphabet size, so from the number of symbols in the alphabet. Okay, thank you for your attention.
Any questions? Okay. There.
Okay, Mauro, I have 2 questions, and I would like to hear your comments on them. They're possibly related. Well, by looking at the results, it seems that the GA does not scale well as the size of the sequences increases. The results tend to be worse than those of the A1 algorithm. On the other hand, when I was looking at your representation and the genetic operators, well, the application of genetic operators leads to infeasible individuals that then you try to repair. But as far as I understood, you rely on standard genetic operators for binary strings. Did you consider developing specialized genetic operators that are able to generate always feasible solutions?
Okay, no, in this preliminary work, no, but is one of the future work. About the first part of the question, it is true that when we increase the value of the sequence length parameter, the performance are not so good. In particular, algorithm A1 perform better than our algorithm. Here in the presentation, I didn't report the evolutionary plot, generation against fitness, but I think that we can improve the performance of our algorithm with by increasing the number of generation, because especially with the value of sequence length equal to 512, the evolution requires more than 1,000 generation. So, but yes, definitely we have also to investigate the definition of new operator and not using the standard ones.
A1, A2, and A3. A3 seem to be the worst. Why did anybody develop A3 from A2? I mean, it should be an improvement. Where do these algorithms come from?
If I remember correctly, the authors of algorithm A2, A3 are the same author. They propose algorithm A3 and then they propose algorithm A2. Here I reported A2 before A3.
Okay.
Yeah.
Okay, maybe any more questions from the audience? Okay, just one more from me. You have mentioned that this problem is important for bioinformatics applications. Do you know of any particular application where you could use this?
No, because this problem was I didn't know this problem before this work, and the problem was suggested by the second author that he works in the field of bioinformatics.
Okay. Thank you. No more questions? Okay, so let's thank Mauro again.
Thanks.
And the next speaker is going to set up the equipment. Okay. Stefania Monica. First name Stefania, second name Monica, unlike the badge. Yeah, presenting hybrid swarm intelligent node location in wireless sensor networks.
So good afternoon, everyone. My name is Stefania Monica, and I am a PhD student at the University of Parma in Italy. I will present a paper entitled Hybrid Swarm Intelligent Node Localization in Wireless Sensor Networks. So we will start by giving some hints and the introduction to the problem, and then we will describe some of the most commonly used localization algorithm, and in particular we will propose a swarm-based approach to solve the localization problem. And finally, we will show some results which have been obtained by implementing the particle swarm algorithm and a variant of it in a MATLAB-based simulator. So let's start with the introduction. The problem I'm interested in is the localization of nodes in wireless sensor networks. In this paper in particular, we consider static node, so nodes that don't move, and we consider indoor localization. The general idea is that you have a big number of sensor nodes, but you only know the position of a few of them, which will be denoted as beacons throughout the paper. And so given the known position of the beacons, we want to estimate the position of the other nodes by means of signals traveling between beacons and each of the other nodes. The main assumption is that we use ultra-wideband signals for internode communication, and this choice is motivated by the fact that, as I said, we are studying indoor localization, and the large bandwidth of ultra-wideband signals allows to resolve multipath component and also to penetrate through obstacles, and these of course are major issues in indoor environments. And given an appropriate number of range measurement between each node with unknown position and the beacons, it is possible to compute the position of the the target node, the node with unknown position. More precisely, from signals which travels between each pair of nodes, one can extract some parameters such as the received signal strands or the angle of arrival or the time of flight. And then from this parameter we can calculate the distance, estimate the distance between each pair of nodes, and then with proper algorithm it is possible to estimate the position of any given node. Here we choose a time difference of arrival approach, so based on the measurement of the time of flight. And more precisely, time difference means that this is based on the estimation of the difference between the arrival times of signals traveling between nodes. This is one of the most commonly used approach in the literature. And in particular, algorithms such as the two-stage maximum likelihood and the plane intersection methods are very known in the literature and are very used for simulation and so. Anyway, we proved that these algorithms are geometrical algorithms, which and each of them involves the solution of systems. And it can happen that sometimes these systems are bad conditioned, so we have numerical errors when computing our calculations. And to overcome this limitation, we propose here an optimization-based approach, and more precisely, we use the particle swarming optimization to solve the problem that we are going to see. First, we need to give some notation, let's say. First of all, we are interested in bidimensional localization, and each beacon will be denoted by SI, and its coordinates are XI and YI, and we suppose that we have M beacons. In the picture you can see that we have, for instance, 4 beacons and only one target. And the target position, the true target position, is indicated as UE, and the final estimated position as at UE. And in case we have, as in a real situation, more than one target, we estimate its position one after another. The true and the estimated distance between the ith beacon and the node that we are currently estimated are indicated as Ri and at Ri. So once again, Ri is the true one, and the at means that this is the estimated one. And according to an ultra-wideband channel model that have been studied, the estimated distance obtained by the measurements is the true distance plus an error, which is the sum of a Gaussian zero-mean variable and a constant, a synchronization bias B. So now we are ready to introduce some of the localization algorithms. As I said before, classically the localization problem is solved by means of geometrical methods. And for instance, the two-stage maximum likelihood method is based on the fact that each time difference of arrival measurement defines an hyperbola. And given a set of the time difference of arrival measurements, the position estimate of the node is determined by intersecting such hyperbolas. At the opposite, the plane intersection method, according to this method, any tripole of beacons identifies the major axis of a conic, a focus of which is the position of the source. And so once again, given at least 2 triples of beacons and so 2 conics, the position estimate is determined by intersecting the 2 or more axes. As I said before, this problem can become bad conditioned in some cases. So instead of treating the problem as a geometric one, we consider it as an optimization problem. So we start by, say, geometrical equations. As a matter of fact, each distance measurement between a given beacon and the current node defines a circumference on which the target node has to lay. And so, given a set of beacons, it is possible to intersect these circumferences and obtain a system of equation in which here you can see on the slide equation 1 is the equation of the ith circumference. And then we use the difference between each of these equation and the first one to obtain the linear system which is represented by equations 2. So we obtain a set of m minus 1, where m, as I said, is the total number of beacons. A set of m minus 1 equations, linear equations, which can be represented by this system. And instead of solving it by means of analysis, let's say, we rewrite it in terms of a minimization problem. And so we try to solve this optimization problem, and as I said before, we are going to use the particle swarm optimization to solve it. Okay, so you certainly all know how the particle swarming optimization algorithm works. Anyway, here I have some hints about that. So the set of potential solution is modeled as a swarm of S particles, and each particle in the swarm at any given instant is associated with a position and a velocity. So with a vector which represents the position and a vector which represents the velocity. The velocity and the position are then updated at each step, and each particle, the updating rule uses the fact that each particle has memory of the past. And so each particle knows not only its own best position, but also the global best position, and the values of the fitness function in correspondence to both its best position and the global best position. These values are used to update, as can be seen from the slide, the velocity at each step. So both the positions and the velocity are initialized randomly at the beginning. And then here you can see the updating rule for the velocity, which is obtained by summing three terms. The first one is the velocity at the previous step, which is opportunely weighted by a multiplicative factor, which is called the inertial factor. And the second terms deals with the ability of each particle of moving toward its own best position reached so far, which is represented by yi. And C1 is the cognition parameter. And so this part is the cognition part. Finally, the third term is the social part, because it deals with the ability of the particle of knowing the global best position. And this is why C2 is called the social parameter. And the global best position ever reached by each particle until instant t is denoted as y. So once the velocities are updated, this is the updating rule for the position of each particle, and the algorithm goes on and on until a stopping criterion is met. And this could be the achievement of a satisfying value of the fitness function, or the reaching of a given fixed maximum number of iterations. So this is the most standard version of the particle swarming optimization algorithm. And in a previous paper, we compared the behavior of this method applied to the solution of our localization problem with the results obtained by using the two methods that I mentioned before, namely the two-stage maximum likelihood and the plane intersection. And we showed that this algorithm could really improve the performance of the other two. In this case, we propose a modified version of the algorithm, and the additional step we introduce is very simple. So at each step of the particle swarming optimization algorithm, we consider a permutation in the set of the indices which characterize the size of the population. And this permutation is so that we order the particles starting from the one which has the lower value of the fitness function. So since this is a minimization problem, the best particle, going up to the particle with the worst value of the fitness function. And once we have made this permutation, we take half of the particles, namely the one with the higher value, so the worst value of the fitness function, and we replace their positions with positions which are close to particles of which have better values of fitness function. So in particular, particle which whose index is p of t plus k is replaced with a particle which is close to the one which has indices p of k. So the updating rule is that the one which is represented by equation 4, where the error, rk, that we had is uniformly distributed in the interval 0, 1, and we assume that they are independent. In the next section, we compare the results obtained with classical particle swarming and the proposed hybrid version. So the performances are evaluated in terms of the distance between the real position of the particle and the estimated one. And we compare the minimum number of iterations which are needed to attain a fixed tolerance, both when using standard particle swarming and the hybrid version. Okay, here is a list of the parameters which have been chosen. In particular, both the cognition and the social parameters have been set equal to 2. And this choice is motivated by the fact that this choice makes the weights for social and cognition parts be 1 on average. And we considered 3 values for the size of the swarm population, namely 40, 70, and 100. And we considered 2 cases. The first case, we took the inertial factor as uniformly distributed in the interval 0.5 and 1. And also we considered the case in which the inertial factor is 0. We made a simulation for 2 different values of the tolerance, namely 10 to the minus 1 meters, and we saw 10 centimeters, and 5 centimeters. This is the first scenario, where you can see 3 beacons at and only one target node, which is quite close to one of the beacons. And here are the results which have been obtained. So the first table refers to a tolerance of 10 centimeters. And you have both the case in which the inertial factor is uniformly distributed in the interval 0.51, and the case in which omega is equal to 0. Observe that this case, this last case allows to obtain very fast convergence when using the hybrid particle swarming. And actually, this is not, it is not surprising that the case with omega equal to 0 goes somehow better than the other case, because setting omega as 0 means that we are not considering the first addend in the previous definition of the updating rule of the velocity. So we reduce the ability of the particle to explore new areas. But this is not a problem for our problem, because this is a convex problem, so we don't have local optima. having a look at this table, you see that as the number of the population, as the size of the population increases, the number of iterations decreases as expected. And if you compare the particle swarming with the hybrid version of the particle swarming, you see that this last one is faster. And especially, as I said, when omega is equal to 0. For instance, with a population of only 40 individuals and omega equal to 0, a tolerance value of 10 centimeters is obtained when in only 3 iterations. The table at the bottom refers to a tolerance which is smaller, so only 5 centimeters. And in this case, when using omega uniformly distributed in the interval 0.51, we have that the particle swarming outperforms the hybrid particle swarming. So it converges faster. But once again, when using omega equal to 0, the convergence of the hybrid particle swarming is much faster. And the same happens with a slightly different scenario. So where once again we have only 3 beacons and observe that this is the minimum number of beacons which is needed to solve the problem. And there is once again only one target, but this is farther from all the beacons. Anyway, the obtained results are qualitative equal to the previous one. So once again, the better case is the one in which we consider omega equal to 0, and we use the hybrid particle swarming. This happens with both values of the tolerance. Finally, here we have a case with 6 beacons, so a bigger number of beacons, and once again only one target. In this case, the behavior once again are similar, but if we compare the results obtained in this case with the previous one, we observe that when using only 3 beacons, the convergence is faster. So since 3 is the minimum allowed, this suggests that 3 beacons is the optimal, say, value that is, it is better to use only 3 beacons to locate each of the node. Maybe in case we have more beacons, we can choose the 3 ones which are nearer to the current target. Finally, we consider a case with 3 beacons and some other nodes which are randomly placed in the space. And here we have a figure which represents the number of iterations for each of the 12 target nodes which are represented here. And as I said before, in case of more target, the position of each of them is estimated one after another. And so here we have the number of iterations needed for each of the 12 target. The red dots indicate the number of iterations needed for when we use classical particle swarming, and the green dots refers to the proposed hybrid version of the particle swarming. These simulations refers to the case with omega equal to 0, which turned out to be the faster case, let's say, and with a population of 40 individuals. As a matter of fact, previous simulations show that increasing the number of individuals in the population does not impact much on the velocity of convergence. So we choose only 40. And as you can see, for all the target nodes, the number of iterations for the hybrid particle swarming is definitely smaller, both in the first case when the tolerance is 10 centimeters and in the second case where the tolerance is 5. So, to conclude, we have considered the problem of ultra-wideband signaling-based localization of nodes in a static wireless network, and we formulated it as an optimization problem, which was solved both by means of the particle swarming algorithm and a slightly modified version of it. We compared the results in terms of the minimum number of iterations which are needed to attain a fixed tolerance. And the simulation results show that the proposed hybrid version of the particle swarming algorithm, in this case, can significantly outperform the standard version in terms of convergence speed. So as a future work, we could extend this work for also three-dimensional static localization. And the fast convergence of the proposed hybrid particle swarming makes it attractive also for dynamic localization. So for localization of moving targets. Finally, it would be interesting to have feedback on how our simulation were accurate with respect to real experimental results. So thank you for your attention.
Thank you, Stefania. Questions? Nope. You have mentioned that in the previous paper you compared PSO with other geometric methods, and PSO was better.
Yes.
And
Could be bad. I mean, in certain situations, also that those methods worked well. If the nodes, the beacons were placed in particularly good positions, I mean. But in some cases, for instance, if the beacons lay on the same line, those methods can lead to badly conditioned metrics, and so the numerical calculation involved in the algorithms is tricky. I mean, it leads to wrong results. While these problems don't arise when using particle swarming optimization, which seems to be more kind of flexible. I mean, you can use it in more situations. I mean.
so, and now you have a hybrid PSO, which is much better than PSO.
Yes,
so
because actually I'm interested. The aim of my PhD should involve the localization of the dynamic targets, so moving objects, and this is why we are interested in fast convergence. And so in this paper, the aim of this paper was to test on static nodes how we could change somehow the standard particle swarming in order to make it faster. Because yes, it works for static node. It's not a problem. It works better than standard geometrical algorithms, and we are not interested in time. So this is not a problem if it takes longer. But the standard particle swarming can take longer than the other algorithms. So making it fast is interesting for us, and this seems a good choice.
So it seems like you already have the best algorithm, also the best method known for this problem.
I suppose not, but at least we improved. I mean.
Okay. Did you try lowering your tolerance level to see if it scales
no.
well?
Not yet.
Okay.
Because these are the values that are okay for us. I mean, if we are wrong of 5 centimeters, it's okay. So we didn't go lower. I mean.
Okay. No more questions? Okay, so I think we are a bit early, but we can move to the last presenter of the session. Let's thank Stefania again. After the last presenter, we will have the closing session here at 6. Nelicia Pele. Great, I did it well. A study on hyperheuristics for hybridizing search.
Thank you very much for introducing me. Thank you for attending the session, the last session for the conference and the session. What I'm going to speak about this afternoon is hyperheuristics, but not in the traditional sense. I'm varying what's previously been done with hyperheuristics, and I'm trying to look at how it can be used to hybridize search. So a quick overview of the talk, just an introduction as to why I've started looking at what I'm looking at. Has anybody worked in hyperheuristics here previously or is familiar with the field? Okay. The hyperheuristic that I'm going to implement is one that uses a meta-heuristic, which is an evolutionary algorithm. And I'm just going to look at some of the problem domains and how it worked in these problem domains, the experimental setup for testing the EA hyperheuristic, and then results and discussion, a conclusion of the results, and then where to from here. Okay. So the no free lunch theorem basically states that if you take any AI method, that method doesn't generalize well over different problem domains. It can work well for a particular problem, or it can work well for a particular instance of a problem. Now, hyperheuristics are a bit of a contradiction to this, because the aim behind a hyperheuristic is to provide some form of generalization. And in recent years, this has been to such an extent that we are now trying to generalize over domains. So I think it was about 2 years ago, there was this cross-domain challenge which looked at developing a hyperheuristic that could possibly generalize over 6 different combinatorial optimization domains. So there's a bit of a contradiction there, and this is what all this work is about. So my aim is to extend the idea of a hyperheuristic even further and look at the possibility of eventually getting a hyperheuristic to choose the best AI method at different stages in constructing a solution. So the work I'm going to present here today is just some initial ideas to eventually lead to this. And what I've done is I've looked at hybridizing search. So the standard search methods that you get in AI, depth first, breadth first, A-star algorithm, hill climbing, best first, these are generally used to solve certain classical AI problems like the 8-puzzle problem or the Towers of Hanoi. And what I've done is I've looked at what happens if you try to hybridize this. What happens if you now get a hyperheuristic that will choose which search to use at which point of solving the problem. And that's what it's all about. So the main aim here is to investigate what the effect would be if you get a hyperheuristic to choose those searches. So just a quick introduction to hyperheuristics. So initially, hyperheuristics were defined as heuristics to choose heuristics. So now heuristics has become a really overloaded word, because you get heuristics that would be a rule of thumb. You get heuristics that are actually meta-heuristics. So the rule of thumb heuristics and the move heuristics we refer to as low-level heuristics. So there's basically 2 types of heuristics that a hyperheuristic chooses or selects. The one is constructive, and these heuristics are used to select which heuristic to use when constructing a solution, so at particular parts of a solution. The best example I can think of is an examination timetabling, when you're trying to schedule exams and you want to actually work out which exam do I schedule next. So you have a number of low-level heuristics that you can use, construction heuristics. So the exam that's involved in the most clashes, the exam that has the most number of students, the exam that has the least possible slots on a timetable. So those are construction heuristics or construction low-level heuristics. Perturbative heuristics do something slightly different. Once an initial solution is created, perturbative heuristics then try to change that solution and improve it to improve the results that you've got with it. So those are the 2 types of low-level heuristics that hyperheuristics have generally been used to select. So we then came along the category of selection construction or constructive hyperheuristics. So hyperheuristics that are used to select low-level construction heuristics. And then similarly, selection perturbative hyperheuristics. So they're used to select low-level perturbative heuristics. So perturbative heuristics are things like swapping or deallocating something and allocating it again, or doing some type of mutation or crossover. The field then developed further, and we then came up with hyperheuristics that can generate new low-level hyperheuristics. And this is usually achieved by combining either comparisons, or characteristics of a problem, or existing low-level heuristics, or using things like genetic programming to come up with new rules. So those were the further two categories, generation constructive hyperheuristics and generation perturbative hyperheuristics. So the work that I'm going to currently speak about today looks specifically at selection perturbative hyperheuristics. So instead of selecting things like swaps or mutation, this hyperheuristic will choose which search to use. So do you use a breadth-first search, for example, at a particular point in creating a solution to a problem, or do you use a breadth-first search, etc.? Okay. So the EA hyperheuristic, so the backbone of the hyperheuristic is an evolutionary algorithm in this case. You could use other methods to drive the hyperheuristic. So the typical or the standard generational control model is implemented. So we start again with an initial population. We then refine that population by evaluating the population and applying different genetic operators to it. In this case, it's the straightforward mutation operator. So just to look at what our initial population would look like. So each chromosome in the population is just a string. And the string is made up of different genes where the gene represents a particular search. So randomly, each gene is created by choosing which search to put in that position, and also the number of times to perform that search. So the different searches that can be incorporated are the depth first search, breadth first search, best first search, hill climbing, and the A-star algorithm. So essentially, it's a combination of the low-level heuristics, and in this case, the low-level heuristics are the different searches. The length of the chromosomes, so they're randomly chosen to be between 1 and a maximum length, and that maximum length is problem dependent, so it may vary from one problem to the next. And as you'll see with the problems that I've worked with, it can have a big effect on whether a solution is found or not. So a typical example of what a chromosome would look like, so the 3H here basically refers to applying the hill climbing algorithm 3 times. That's then followed by the best first search, which is performed once, and then the best first search again, which is performed twice. So you can actually have a search being performed sequentially with one gene having the same search in it as the gene before it. The number of iterations as well, that's randomly chosen to be between 1 and a maximum limit again, which is problem dependent. So that's essentially what a chromosome looks like. So that initial population then goes to the standard processes of evaluation and regeneration for each generation of the evolutionary algorithm. And the way in which a chromosome is evaluated is by using it to solve a problem. So if you look at this chromosome again, it's very similar to the previous one. So what would now happen is, in this case, 2 iterations of best first would be performed. So if you have a problem, it usually has an initial state and it has a final state. And with these classical AI problems, the aim is usually to get from the initial state to the final state and produce a solution, or to produce the path of getting from the initial state to the final state. So the initial state will be fed into the first search, and then different searches, so in this case, the first search is the best first, and then different searches will then be applied sequentially until either a maximum number of generations is reached or a solution is found. If a solution is found prior to the execution of all the genes, the process is stopped and the solution path is returned, and the chromosome is then truncated because you don't need additional search to find a solution. In order to ensure that there's consistency and the searches are not being started or restarted each time that there is a new search or a new gene being implemented, a memory keeps track of what state you're at. So there's always the concept of a current state. Initially, the current state is the start state of the problem. And then as you move from one gene being applied to the next, the last state of that search or of that gene forms the current state and the next input to the next gene. So for example, after 2 iterations of the best first is performed, that resulting state will then form input to the 1 iteration of the breadth first search, just to ensure that you're not losing the information of the search that's being performed. So that's the population evaluation. In the study, only mutation was used. Crossover was tested, but it didn't appear to be that effective. So I went with just mutation. So what mutation does is it randomly chooses a gene, and then it mutates the gene by randomly choosing a new low-level heuristic or search, and randomly choosing the number of iterations. And then the new gene is replaced by the newly created gene. So if we look at an example, suppose that was a parent that was chosen. The method of selection to choose parents is the tournament selection. So the straightforward tournament selection that's used with mainly in GP applications has been used in this case as well. A gene is randomly chosen, and that's equivalent to your mutation point, which you normally get. And the gene at that point is randomly changed to be something else. So that's the overall EA hyperheuristic. It was tested on 2 problem domains, and the problem domains were chosen to be domains that the standard searches are normally applied to. So the 2 domains, one's the 8-puzzle problem. I think most people are familiar with the 8-puzzle problem, and you've come across it somewhere along the way. So the whole idea behind the 8-puzzle problem is, in the AI version of it, you're not actually moving the tiles. Is everybody familiar with the problem? Okay. So the whole idea here is you're not moving the tiles, you're actually going to move the space left, right, up or down. So if that was an initial state and you applied a move right, would move the space to the right, up would move the space up. So that's one of the domains that it was applied to. The second domain, again, was the Towers of Hanoi problem, which is also a very, very well-known problem. The idea is to move pegs from one pole to the next, and only one peg can be moved at a time, and at no stage can you place a bigger peg on a smaller peg, moving it from one pole to the next. And then eventually you need to get all the pegs onto the final pole. So those were the 2 problems it was tested on. Just the experimental setup. So a problem set of 20 problems were used for the 8-puzzle problem, and these varied in difficulty. These were obtained basically online from different papers or assignments online or repositories of problems where they did exist with the 8-puzzle problem online. For the Towers of Hanoi, 5 versions of the problems with different disks were used, and that ranged from 3 to 7 disks. The heuristic to be consistent now, also not to bias any of the searches. For example, the A-star algorithm works very, very well with the Manhattan heuristic for the 8-puzzle problem. So to ensure that there's some level of generality, the same type of heuristic was used for both problems. And basically the heuristic was, in a way, just a count of how far a particular state was from a goal state, because the goal state is always known. And if you're dealing with a particular state, you always know what that state is. So for the 8-puzzle problem, it was basically a count of which tiles were not in the place that they had to be in. For the Towers of Hanoi problem, it was a count of the number of rings that were not on the goal pole, and that was given a higher weight. That was summed with the distances of the rings from where they should be, and that was given a lower weight. And that was used as a heuristic. So basically, if I had to define it generally, it's basically a measure of how far a particular state is away from the goal state, and that was also used as a form of fitness as well for the fitness function. Again, because of the stochastic nature of EAs, 10 runs were performed of the EA hyperheuristic. So the parameter values that were used for the EA, these were performed by conducting some trial runs. And that was the population size, tournament size, maximum string length, or maximum chromosome length, a number of iterations, maximum number of iterations, and maximum number of generations. Sorry, that should be 50 for the maximum number of generations, not 10. Okay. And the same in the slide. So here the parameters are basically the same. The only difference was with the number of iterations in the string length. And this was mainly because the Towers of Hanoi problem required more moves to find a solution than the 8-puzzle did for the puzzles that we had looked at. So the maximum string length and the maximum number of iterations needed to be higher. So if we look at the results, I'm looking at them in sets of 10, firstly for the 8-puzzle problem. So as you can see, just to give you an idea of how the EA hyperheuristic performed according to the traditional searches. The EA hyperheuristic, sorry, I've left out some of the values here at the bottom. But the EA hyperheuristic generally if we compare it to the depth first, best first, breadth first, hill climbing, and the A-star algorithm, you can see the depth first did not perform as well. The breadth first performed fairly well, and it was able to provide the minimum number of moves. Best first and hill climbing performed well, but the number of moves were not the minimum. The A-star algorithm performed well, but was not able to find solutions for this. I think this is, 30 and 31 here, for these two problems which were cited as the most difficult in the literature. If you look at the next slide, again, for these problems, the A-star with the sum of tiles out of place did not perform that well, but it was able to find the optimal solutions for the remaining problems, and same with the best first. And the depth first searches and the best first search and hill climbing, you can see the depth first was the worst. Best first and hill climbing found solutions, but not with the minimum amount of moves. If we look at time, each algorithm was given a maximum of 5 minutes to run. And the AA hyperheuristic was able to find solutions in the maximum of about 7 seconds for the most difficult problem. So that's 7 seconds for all, so if you multiply it by 10, it will be 70 seconds for all 10 runs. But if you're taking one run and you're performing it, it found a solution on every run. So if you're performing one run, we're looking at, for the most difficult problem, 7 seconds. For the towers of Hanoi, just to go back to that slide, if we look at generations in which the EA hyperheuristic found solutions, the generations were within 50 generations. For the very simple problems, obviously it found a solution during the initial population generation, but for more difficult problems it needed more generations, but it was within 50. I think the highest generation was about 44. For the Towers of Hanoi problem, again, you have similar performance. The A-star algorithm performing the best together with the best first search and finding the minimum number of moves. Depth first and best first and hill climbing also finding solutions, but not the minimum. And here's where there was a bit of a problem with the EA hyperheuristic. The termination criteria that was used was, as soon as you find a solution, the algorithm terminated. So what happened with the Towers of Hanoi problem, all the solutions were found in the initial population. So there was no time to optimize the actual string further to find one that maybe possibly had the lower number of moves. So for every single run of those 10 runs, a solution was found during initial population generation. So for the AA hyperheuristic, it looked like even if you just used a simple hyperheuristic of randomly creating combinations of heuristics and accepting all moves, it would work. But if you wanted the minimum number of moves, I would have to now force additional optimization and possibly make the AA hyperheuristic run for a preset number of generations rather than saying when a determination criteria should be when a solution is found. So just the overall discussion. So generally the AA hyperheuristic found solutions for both problems. It was able to find optimal solutions for the 8th puzzle problem, and the solutions were actually quite good in the sense that they were optimal. It could find solutions that the A-star algorithm and the breadth first search couldn't find with the sum out of tiles out of place for the 8th puzzle problem. So it did quite well there. So it found optimal solutions. For the Towers of Hanoi problem, the problem was determination criteria, which I'm going to go back and look at and just leave it running for generations and see what it does in that case. An example of one of the heuristic combinations evolved, and this was an example for the 8 puzzle problem. The heuristic combinations were also found to be very different for each run. So it seemed to actually adapt the solution it found, taking all things into consideration, including random noise. So for the 10 runs, different heuristic combinations were found. What was interesting to note that all the heuristic combinations for the 8-star puzzle problem began with the breadth first search first. So it used some type of admissible search first. And then the other ones seem to be, other different types of heuristics seem to be used in the rest of the solution or creating the solution. What was also interesting is that I couldn't say that only these heuristics are used. Each string had a different combination of heuristics, but there definitely seemed to be a pattern with what it began with each time. And there's possibly something that needs to be investigated further to look at possible patterns in the heuristic combinations. But certain searches clearly make a bigger impact early on in solving the problem than later on. Okay, so conclusion. So the main aim of the study was to just see what would happen if you try and hybridize search with the aim of, in the future, trying to look at hybridizing different AI methods. And generally, the AI hyperheuristic seemed to work quite well. It was interesting to see the types of heuristic combinations evolved and the fact that it was different for each run, which means that it was adapting to random noise. It was also interesting to see that there are certain patterns which need to be looked at further. So future work to readdress the termination criteria for the Towers of Hanoi problem. Also looking at different heuristics, because I've used one heuristic generally across the board. What happens if you change the heuristics? How does it affect the searches? And do you put that in and optimize that as well at the same time? So the actual construction heuristics used. Also testing this on additional problems and then looking at additional methods. So moving away from just using the standard searches, including things like taboo search, variable neighborhood search, and possibly to some extent GAs as well. Okay, thank you.
Okay. I don't need to ask if there are questions.
I have one question actually and one comment. The question is it possible to seed the initial population of EA hyperheuristic or something similar in such a way that in the initial population there are all the standard algorithms in their simple form, and then use elitism in such a way that in the worst case you return the best of them and you cannot be overperformed by one of them. And then I don't know if you want to answer and then I say the comment, or if you want to comment.
So in the initial population we could seed it so that each chromosome has all the standard and then it actually evolves it. Yeah, I haven't tried that, but I think that it'd be interesting to see what happens with it.
And the comment is just about the first line of the first slide. You are not contradicting the Nofre-Lange theorem at all, right? Also assuming that EA hyperheuristic is able to always to find the killer heuristic, it takes time to find it. So that heuristic will outperform EA hyperheuristic, okay? And so the average probably of the performance will be the same as all the others. Thank you.
Thank you.
Comments?
Well, I have firstly something that I would like you to clarify, because I didn't completely understood it from your presentation. When you, for instance, have the A star in your chromosome, does it mean that you apply the A star, for instance, to select the whole A-tile puzzle, or you are just applying it one step to move the space to another position?
So for example, if I had 3A,
yeah,
it will perform 3 iterations of the A star. Okay. And then that will remain in memory. And suppose the next chromosome was B for breadth first, it will then be applied to that state, and it won't restart.
Yeah, okay, because something puzzled me when I was looking at your results, focusing on the A-tile problem. The performance of the hyperheuristic is almost identical to that of A star, which somehow makes sense. So it puzzled me. By inspecting the solutions that you achieve, do they somehow say, okay, if you need to solve this problem, then you must apply A star? Or do you have a combination of heuristics in the
solution strings that are evolved? There's a combination of heuristics.
Okay, because
for all 10 runs, they seem to start with the breadth first search, and then after that there's a combination. The one that I just... this is one of the examples of them. Okay. So that would be breadth first, depth first, A star, breadth first, and A star.
Okay.
So there were no strings that had just A star throughout. Okay. They could have been in the population, but I just looked at the best individual each time.
No, just two short notes. Well, you just rely on mutation to do the evolution of hyperheuristics, and I think it somehow makes sense. But I was expecting to see some kind of a mutation operator that somehow moves subsequences of heuristics from one place to another. For instance, if you have a solution in which the first part is not good to solve that particular problem, maybe on a later stage of the chromosome you have a nice subsequence. Maybe you could displace it to the beginning.
So you just take a subsequence and
did you consider any kind of mutation operator that does
I
this
haven't
kind of
played
move?
with that. That's a good idea. I'll have a look at what the effect is. So do you keep a fitness of each subsequence, or do you just do it randomly?
No, you can do just some random
randomly?
mutations and see if that helps to find better solutions more efficiently.
Yeah.
And finally, you started your talk by mentioning that generalization was somehow an important issue for hyperheuristics, and that in a sense is true. So I was expecting to see some kind of experimentation where you took a solution that is evolved with a problem and then apply it to other problems and see if you can also see if there is any kind of generalization from one problem to another. Did you try any of this?
I haven't tried that as well either. To try cross domains for the problems. Okay, thank you.
Okay, more comments? Questions? No? So let's thank Alicia again. And this closes Alia. And I guess we have to wait 10 minutes for the closing session. One of the chairs is already here, so see you in 10 minutes.